Hello, so let's continue our random walk. We start at the origin. It's a walk on the integers. It's one-dimensional. Hopefully today we will be able to talk about a multi-dimensional random walk. But this walk is one-dimensional, so it is on the line containing the integers. We start. I mean, the starting position is not really important, but the convention is that we will start at 0. And then basically the value of the Markov chain at instant n is the sum of IID random variables. So those guys are IID, and they are steps plus or minus 1, which means that if you are at integer n, or let's say k, then basically you have two options. You basically go to k plus 1 with probability p, or you go to k minus 1 with probability q. And p plus q is equal to 1, which means that these are the only possibilities. You cannot take basically move from k to k plus 2, and you cannot basically remain in the same state. So you have to make a transition either to the left or to the right. Okay, so the step is plus or minus 1. Okay, and this will be important. Basically, you can show, you make an argument that x of n is a homogeneous DTMC. The state space is the set of integers, and any state is accessible from every other state. Okay, and so it means that you can always, you can always find, an instant of time at which basically the transition probability is strictly positive. Okay, and we talked last time about things that for example, that the value of x of n, which basically gives you your position on the at what integer you are at instant n. Basically, the value of x of n is, for example, if it's k, so if xn, if x or j, so if xn is equal to j, then it must be the case that j is less than or equal to n. And I mean, because if you start at the origin, then the most you can do in the positive direction is basically to have all the d's equal to plus 1, and in that case you will reach n. If all the d's are minus 1s, you go to minus n, but you cannot go further than that. Okay, so j is less than or equal to n, and n and j, they have the same parity. And it's a very simple elementary school argument that basically these are odd integers, and so if and the sum of an even number of odd integers is even, and the sum of an odd number of odd integers is odd. Last time we basically did an adventure using the transition probabilities. We focused on basically the transition probability B00 of n, which is the probability of being in state 0 at instant n, given that we start in 0. Let's now basically study the system using the first passage probabilities. Again, it's another perspective, and we will pretend as if we don't know what is going on. So as if we will discover what the classification of states is. So now the focus will be Fij of z. So it's the generating function of basically of the random variable Tij. And the random variable Tij gives you the number of steps that are needed, to enter into state j for the first time, starting from I. Okay. Now, so this is the generating function, and you can write it as an expectation of z to the power Tij, where Tij is the number of steps again to enter j for the first time from I. Okay, so doing this, we started basically at the end of the previous lecture. We started doing things like F00, F01, and so on. So F00, you go from 0 to 0 and enter into 0 for the first time. And the trick is that you basically condition also on Z1. Okay, so you start with expectation Z to the power T00, again, which T00 is this random variable that tells you the steps from 0 till you enter into 0 again for the first time. What you can do is that you can condition on Z1, and if you start at the origin, well, you have only two possibilities for X1. So X1 is either 1 or -1. That's it. By the construction of the random walk, so we can condition also on X of 1 is equal to 1, and of course if we do this we need to multiply by the probability that X of 1 is equal to 1 given that X of 0 is equal to 0, and this probability is simply P. And then here the second term, I mean this is the other possibility that X of 1 is -1, and we need to multiply by the probability that X of 1 is -1 given that X of 0 is 0, and this is the Q probability. Okay, and then now you are basically at 1. Now you took a step, so basically conditioning on this X0 is 0 and X1 is 1, it means that you took already a step from 0 to 1, and now basically the remaining steps till you enter into 0 again are basically the number of steps that are needed to go into 0 for the first time, but now starting from 1. And of course this 1 here is this step that you made to go from 0 to 1. So I can now write, conditioned on X1 is equal to 1 and X0 is equal to 0, I can take this T00 and write it as 1 plus T10. So it is 1, which is the step taken from 0 to 1, plus the time now needed to go from 1 and enter into 0 for the first time. And for the other expectation, basically this will be 1 plus T of -1 comma 0, because there is a step taken to go from 0 to -1, and then there is the number of steps needed from -1 to enter into 0 for the first time. Okay, and so when you do these things, you typically get those Z's. Okay, and once you solve like a number of problems, you will not have like to write down these things in explicit detail, and you will find that you can write down basically something like this, sort of automatically. So you say, basically F00 of Z, so it's like you are at 0, then with probability B, you go to 1, for probability B, you go to 1, so that's one step. We are computing a generating function, so basically it's Z to the power, so it's Z to the power 1, and now you are in state 1. Then basically you need F10, and then with probability Q, you will make a step, but this time you make it to -1. Okay, so there is one step now, Z, so this will give you a Z in the generating function, a factor of Z, which comes from here. So this is like what is happening under the hood. But again, like once you get into this business, I mean, you can. So I won't bother like if you start writing down things like directly, so long as you get them correctly. I mean, I have no problem. And this will be F of -10 of Z. And again, this Z here is, it's because of the step that is taken to go to either 1 or 0. Okay, well, nice, but sort of useless. Apparently, it's useless. I mean, now we have this guy, but it's now in terms of this one and this one. Okay, let's try something else. F01. So this is the number of steps. So this is the generating function of the random variable, which is T01, which is from 0, you enter into state 1 for the first time. Same trick. Condition also on X1 equals 1, and then have the probability X1 is equals -1 and multiply by the probability that X1 is -1 given, so this should be given X0 is equal to 0. Okay, and then 0, you go to 1. 0, you go to 1. So what is T01? Now T01 becomes 1 almost surely. So with probability 1, this is 1. Okay, so with probability 1, so this random variable T01 now, given that X of 0 is 0, and given that X of 1 is 1, now this guy is 1. the number of steps to enter from 0 into 1 for the first time, well, it happened in one step. That's it. So it is 1, okay? And so it says z to the power 1. Z to the power 1, and this guy is equal to p, so you get this term pz. And then for the other term, then you go to you go now to -1. So basically we need this guy's q, and then this here will be 1, the step that you make from 0 to -1, and then t minus 1, 1, the number of steps to go from -1 and enter into 1 for the first time. So now it is like this. So it is pz plus qz f of -1 to 1 z. Okay, so now it's a bit better than the previous case because, like, there is a term now without an f function, which is like this pz. But let's think about the problem. So the problem has symmetry. I mean, you can show these things like a bit rigorously, perhaps like by studying the f probabilities. But I don't think it's difficult to see that f01 of z is actually fi plus 1 of z. What is is there any fundamental difference to go from 0 to 1 or to go from I to I plus 1 and enter into I plus 1 for the first time? What you need here is basically that you go from a state to the state to its right, and that's it. And remember that basically the state space is the number line with the integers on it. Okay, and so if you send it any integer, like basically the view is the same. Okay, so f01 of z is fi, and again, like you can study the probabilities I plus 1 of n. Okay, and basically if you study these probabilities, so if you are at I and this is I plus 1 and this is I minus 1, what is fi I plus 1 of 1? So what is the probability that you go from I and enter into I plus 1 for the first time in one step? So that's p. See, it's p. Regardless of what so it's because the process is characterized just by a p and q, so it does not depend. So for every k, you go to the right with probability p, to the left with probability q. So basically this, just from my first step, it's clear that things will not depend on I. Okay, but I mean, so what is fi I plus 1, and then let's say 2. So you enter into I plus 1 for the first time from I in 2 steps. Well, this is 0, right? It can never happen because, like, you either enter in one step. The other thing is that you go to this in that other direction and you go into I minus 1. Well, now you need 2 steps to go into I. So there will be an f of I plus 1, and then in 3 steps. So this will be what? This will be that you do a step like this. So that's q, and then you do a b and p, and so it's qp squared. And then you can continue playing this game. After that, there will be like possibilities, and then you start getting a sum. But the interesting thing is that you will get basically quantities involving p and q, and it does not depend on r. So if you compute the generating function of this quantity here, it does not really depend on r. It is exactly the same regardless of I. So this is basically the reason that f01 of z is fi I plus 1 of z. Okay. So keep this in mind. It's useful, for example, like if you have something like f minus. So one application that will be needed shortly is f minus 1 and 0 of z is the same as f01 of z. Okay, from -1 to 0 is like from 0 to 1. Okay, now f minus 1 of 1, again, like this guy's pz, and there is no f function here, but there is this one here. And so we want to show actually that f minus 1 of z is f01 of z multiplied by f01 of z again. So it is f01 of z squared. Okay, because if this is true, if this guy is equal to the square of this guy, we will have an equation involving just one of those f generating functions, f01, and then you can obtain it. And then, as we will see later, we will obtain f minus 1, 0 in an easy way, and then we can obtain something like f00 of z. Okay, so now the hope is that f minus 1 1 of z is actually can be actually be exactly expressed as f01 of z squared. Okay, and then this will allow us to have one equation in one unknown, which is f01 of z, and so you can obtain a closed form expression for f01 of z. Okay, so what is the story here? The story is that f minus 1 1 of z is basically so to go from minus 1 to 1, again from the structure of the Markov chain itself. There is no way whatsoever, there is no other way to go from minus 1 to 1 except by entering first into the state 0. Okay, so t minus 1 1, you can surely write it as t minus 1 0 plus t 0 1. Again, because you do not allow transitions except to the immediate neighbors to the left and to the right, and between minus 1 and 1 there is 0, and so you need to basically go through 0. So t minus 1 1 is t minus 1 0 plus t 0 1. Okay, and now again it's like a game that we played here, but it's like a bit more complicated. So initially here I conditioned on things like x1 and x1 is equal to 1, x1 is equal to minus 1. So let's see what we will do here. So what I will do here is that I will condition on basically this t minus 1 of 0 being finite. So it means that the event here we are conditioning on is the event that basically in a finite number of steps, no matter how large, you will, starting from minus 1, enter into 0 for the first time. So this will happen basically in a finite number of steps. So I will, so basically what I'm doing here is that I am conditioning on t minus 1 0 being finite. And there will be another term. So again, like this thing looks like, total probability. You can call this what I'm doing here as above, law of total expectation, whatever you want to call it. I need also another term, t minus 1 0 is equal to plus infinity. Remember, first passage probabilities are stop times, and stop times can be plus infinity. And because we are trying to obtain the f probabilities, we are pretending that we do not know the classes of the states. So perhaps the states are transient. And between you and me, we know from the previous lecture that if p is not equal to 1/2, then the random walk basically has all its states being transient. So again, like if you are doing this to a Markov chain that you have not encountered before, you must be open to the possibility that basically you are dealing with transient states. And in that case, it may be the case that 0, for example, is a transient state, and starting from minus 1, you will never ever enter into 0 for enter into 0 in a finite number of steps. Okay, so the two possibilities will be t minus 1 and 0 less than infinity, t minus 1 and 0 is plus infinity, and also we will condition that, of course, x of t minus 1 and 0 is 0. Okay, so the event is that you will enter, this is that at this time instance you are at 0, which is by definition x of t minus 0 and 1. T minus 0 and 1 is this random variable that tells you that the number of steps that are needed to go from minus 1 to 0 and enter into 0 for the first time. Okay, so the conditioning here will be on x of t minus 1 and 0 equals 0, and t minus 1 and 0 is finite. X of t minus 1 0, x of t minus 1 and 0 is 0 again, which means that you are at this, you reach 0, which means that you have reached 0 from minus 1, but now basically this happens at an infinite time. And of course, you need to multiply by the probabilities. So here is the nice thing about generating functions. We typically, when we do generating functions, we we assume that, at least in what we're doing in this course, that Z is, you can make Z complex, but we focus basically that Z is like a number between 0 and 1, and 1 is not in the business, is not there. So basically, if we want ones, we take limits. Okay, so we do not so we typically assume that the generating function is not even defined at 1, but we can take the limit as Z approaches 1, and we can exploit something like Abel's limit theorem. Okay, so the idea is that if Z is in this range, then its magnitude is less than 1, and if this guy here is plus infinity, then that's 0. Okay, so you have a number that is less than 1, and then you raise it to infinity. So basically, it is multiplied by itself an infinite number of times, so it will die. Okay, and so the nice thing is that this second annoying expectation will basically be equal to 0, again, because we are taking expectation of Z to the power something, and Z will be in this range. And so we are left with the first expectation, in which we condition on t minus 1 and 0 being finite. And now, you may wonder, so in f00, conditioning on x1 equals 1 and x1 equals minus 1 sort of makes sense and is not that problematic. But what is the business here? The issue here is that I want to make use of the strong Markov property. Okay, the strong Markov property. So, what is the strong Markov property? So, as a reminder, the strong Markov property tells you that if t is a stopping time with respect to the Markov chain. Okay, the probability that x of t plus 1 is equal to I1, x of t plus 2 is equal to I2. Up to x of t plus v is equal to iv. Okay, so those are basically x of t plus 1, 2, and till v, where v is some finite number, and h, which is an event that is specified in terms of x of 0 up to x of t minus 1. Okay. And you have this probability, and you want to compute it given that t is less than infinity. So the stopping time is less than infinity, and that x of t is equal to I. So this stopping time, x indexed by the stopping time, is equal to I. So remember, we did the proof of this one, which is very important. That basically this probability is probability that x of 1 is equal to I1, x of 2 is equal to I2, up to x of v is equal to IV, given, so this x of t is equal to I will be x of 0 is equal to I, times the probability of this event h, given that the stopping time is finite and that x of t is I. So basically conditioning on these two guys, h and those are independent. So basically, like the simple way of saying it is that the Markov property is also satisfied. So it satisfied the future and the past are conditionally independent given x of n. So give me events in terms of x of 0 up to x of n minus 1, and then give me x of n. Then any event in terms of x of n plus 1, x of n plus 2, and so on, will be conditionally independent of x of n minus 1, x of n minus 2, or any event defined in terms of these, given that x of n is specified. The strong Markov property tells you that you do not have you do not need to condition on x of n is equal to R. If you replace x of n by x of t, such that t is a random variable, but not any random variable, a stopping time, then in that case, the Markov property holds. And so you can decouple, you can basically say, given these, you can write down the probability as a product, okay, and you can, it's as if the chain has started in I, so if x of t is equal to, as if this chain is started in I, and then you go to x1 equals I1, x2 equals I2, and so on, multiplied by the probability of the other, of this H event, given that t is less than infinity and x of t is equal to 1. Okay, and so there is, we took actually the formal proof. The idea of conditioning on basically this guy here and this one is to apply the strong Markov property. And the strong Markov property will tell you that, let's put it, so given these, basically you can split, so basically there are things that futuristic, okay, so this is basically future. Okay, so you start from -1, and your stopping time is this first passage from -1 to 0. This is like future, okay, and so you can write it. So this is the expectation of z to the t, z to the power t01, given that x of 0 is equal to 0, basically based on this event. So you have reached 0. So it's as if now you are restarting your system. It's as if you are sort of restarting your Markov chain now, like the initial state is 0, and you ask, how many steps do I need to take to enter from 0 to 1 for the first time? You know that, basically if random variables are independent, the expectation of the product is product of expectation. So think of this as product. Okay, so this is t of -1 and 0 multiplied by z t of 0, 1. Now I can split the expectation because of the independence. And I know that specifically it is conditional independence. And I know conditional independence because I am applying the strong Markov property, okay? So I am making use of it. And so basically I can split this guy and condition on x of 0 is equal to 0. And then it's exactly like here. Exactly like this one, and then I will have z to the t -1 and 0, z to the t -1 and 0, and then you have, so the other guys will remain the same, and then you have this probability that is here. So basically you did this trick so that you can apply the strong Markov property, and then you need like sort of like simplify things again. And so what you will do is that you can basically add a term, an extra term that is equal to 0. So you will basically have a term that looks exactly like this one, a term that looks, so focusing on this second, this second expectation here, you have a term that is basically exactly equal to it, exactly the same, except that here, if here we have this is finite, this is infinite. So this extra term that I'm having, of course, like you cannot just insert the extra terms, but it's 0. In our case here again, it's 0 because this guy is infinity and z is strictly less than 1. And then we have multiplication. So again, like we have this term here, and there is a probability. I don't care about what this probability is. I will not bother about even thinking about it. But it is multiplied by 0, so the overall term is equal to 0. And so what I have here is equality. I mean, there is nothing. And the idea here is that now we can remove the conditioning, right? We can remove the conditioning and just keep the conditioning on x of 0 is equal to 1. So it's the first step in reverse. But we needed the first step to basically use the strong Markov property and do the split. And so now we have these two expectations like this. And so one of them is f -1 and 0, and the second one is f01. And so now, by this claim that I made before, I'm lost. This one here, that this one is also f01 of z. And so this is the, basically the square, and so we have an equation. So we have an equation for f01 of z, and it's a quadratic equation. Okay, it's a quadratic equation which we can solve, and we'll do so. Okay, so it's very nice. If you did not like this, Okay, so here is another proof. Okay, I will not go through it. I mean, it's again, it's for you. Here is another proof in which, like, it's a proof that is tailored for proving, proving this identity here, and without like making use of the strong Markov property. Okay, so these things are nice, and again, it's like you do them. It depends again, like sometimes basically you need like to see things like in very slow motion to make sure that you understand what is going on. But this level of so let me emphasize again something. This level of detail is not needed. Like, so when it comes to, like, let's say homework 13, homework 14, again, you can be a bit more pragmatic. But I am providing those again because sometimes they are important, that you see actually why things are behaving like this. Okay, but as I explained in F00, like you can like let me do it again, like here. So F01 of Z, then how can you write this thing? So F01 of Z, then you want to go from 0 to 1. Well, starting from 0, you can go to 1 with probability B. That's one step, and you are already in 1. That's it. Or you can, with probability Q, go to -1. But now, if you are at -1, now you took a step from 0 to -1, and now you need to go from -1 to 0. And what is this thing? This thing is basically to go from -1 to 0, and then from 0 to 1. And then this is equal to that in our particular case. And so this is actually F0 of 1Z squared. If you see something similar, you can just basically write down those couple of lines. But again, it's also important like to have knowledge of what is going on. Okay. So I think the solution of the quadratic equation is next. Okay. Any question? Okay, so we have this one, quadratic equation. So apply the formula. That's it. An explicit formula for F01 of Z. An explicit formula. Amazing. Still, there is a tiny problem, which is like when you solve this quadratic thing, that you have the two signs. You have plus and you have plus and minus, and then you need to think about whether or which one should be like kept and which one should be rejected. And so let's think here about what is going on. Suppose that you take the plus sign. The plus sign, then F01 of Z is equal to 1 plus square root 1 minus 4pq Z squared over 2qz. Now suppose that you put Z equals 0. Okay, so if you put Z going to 0, what will happen? So this in the numerator you will have 2, right? So you'll have this Z squared will be 0, and then you have 1 plus 1, which is 2. But then you have Z in the denominator, so this thing will explosion. So you'll have explosion, right? But in the generating function, if you put Z equals 0, what you should get is basically 0, right? So for the F probabilities, and so you should get a 0. You should get a finite number. Actually, it should be 0. So the idea here is that we should have a minus sign. We should have a minus sign. And again, like if you want to go the extra mile, then basically you need to check. Take the limit using L'Hopital or something. I mean, now if you have a minus sign and you try to set Z equals 0, basically you will be in a 0 over 0 situation. But at least this gives you hope. If you put the plus sign, there is no hope. It's 2 over 0. It's infinity. But with the minus sign, there is hope, and you can check. Okay, so you can apply L'Hopital or something like this, and discover that yeah, it is the minus sign. Okay, so that's the solution. That's F1. That's F01 of Z. Okay, and this is going from 0 to 1. Okay, and so it is the same thing. So basically, going from I to I plus 1. of z is what? Exact same thing. It is just f01 of z. To go from I, to go from a state to the state to its right. I mean, is, given that the states are infinite, they live on, they are integers, they're integers. Will it make any difference to go from 0 to 1, I to I plus 1? No, nothing. And again, like you can, as I tried to do on the previous slide, like go and try to find what is I plus 1 of n. And you will discover, that you are writing probabilities. All of them depend, you will have sums with terms involving P and Q, and I will not be there. Okay, so basically this is not just f01. It is also f minus 1 and 0. It is also f17, 18, and so on. And from the we proved that. So we proved that on the previous slide that f01 is f01 of z squared. Okay, so we did this proof, and now you can generalize it. Okay, because rather than having minus 1 and 1, you can go like from I to I plus 2. Okay, or here I wrote it down. You can go from m to m plus v, but if you go like to m plus v, then you need to raise this thing to v. If v is equal to 2, then you have 2. Again, this is basically what we did on the pre. So you want to go like from any state. Again, you can show it. You can show it rigorously. You can either do a tailored proof without referring to the strong Markov property, or you can use the strong Markov property. Okay, the strong Markov property tells you that the future and the past are conditionally independent given the value of given the value x of indexed by stopping time. So this is the thing here. So you go from m to m plus v. You will have to go from m to m plus 1. You will have to go from m. So this is like sort of the intuition. You need to go from m to m plus 1. And then given this, you need to go from m plus 1 to m plus 2. Given this, so once you reach one state m plus 1, then you can basically by the strong Markov property say, well, it's as if I'm starting here. It's as if I'm starting here. Okay, and the events become independent. And so for generating functions are like Laplace transforms, are like Fourier, like the characteristic function, moment generating function. Basically, if you have independent things that are summed, basically the generating function will be multiplied, right? So the time to go from m to m plus v is m plus 1 plus t m plus 1 m plus 2 and so on. Okay, so you have the times added together, and those times again you can basically do things such that you get the generating functions multiplied, and the justification can be the strong Markov property. First message is stopping time. And so basically, anything that involves stopping time, you can basically do the same thing. Now, what about f01 or f1, 0? Rather than inventing the wheel, you can basically make the following argument. What is really the difference between going from 0 to 1 and going from 1 to 0? There is no so basically moving from I to I plus 1 or from I plus 1 to I. Basically, the thing is that like P and Q are interchanged. The rules are interchanged. So again, in our chain, because like it's going on, along the line of integers, then basically you have this. You can exploit these ideas and say, in some, I think I will give you in homework 14 something in which like you basically you walk only from 0 to and the positive integer, something like this. Sometimes what I'm saying here will not be applicable, but here, yes, f10 is F01. You just interchange the roles of P and Q. If you find the P in the expression, replace it by Q. If you find the Q, replace it by P. That's it. There is nothing fundamentally different, right? So this will be this will be F10. You just go to this expression and replace P by Q and Q by B. And now from the previous slide, we have an expression of F00 in terms of F10 and F01. Now we know both guys. So now we know F00. And again, because all the states look the same, they look the same, it is FMM of Z. We have now the generating function of the first passage time from a state to itself. So this is the generating function of the random variable, which is the amount of time or the number of steps taken starting from 0 to enter into 0 again for the first time. So we have an expression, and now you may try to basically take like the inverse Z transform and get things in the probability. You can get F00 of n. Okay, but we can use Abel's limit theorem and basically make conclusions based on taking limits as Z goes to 1. Okay, so basically this is the beauty of Abel's limit theorem, that you can do your business without bothering about the inverse transform. But I think actually the inverse transform here is doable, and it has like it has a closed form. Okay, so how do we classify things based on the F probabilities? So actually, this is this is how I explain things in the when we talked about the classification of the states of a discrete time Markov chain. I said that Fjj, if Fjj is 1, then the state is recurrent, and if Fjj is strictly less than 1, then the state is transient. Okay, and so how can you take this one? So basically, Fjj is the summation of Fjj of n. Okay, so it is this summation here. And again, it's this summation here is because it's a summation of non-negative terms. Then by Abel limit theorem, basically you can obtain this summation here by taking the limit of this guy as it goes to 1. And the nice thing about Abel's limit theorem is that this limit in the Z domain, if it is plus infinity, so even if it diverges, if it's plus infinity, then the summation is actually equal to plus infinity. Now, we are talking about F probabilities. It will never be the case that this summation will go to infinity, but even in other cases, like if you are doing this game of taking the limit as it goes to 1 to a summation involving the transition probabilities, well, if you get infinity, then the summation in the time domain is also infinity. Okay, so take the limit. So we need to take the limit as that equals, basically the square root is a continuous function. So taking the limit here is, you can move the limit under the square root, and you can set this z equal to 1. And if it is equal to 1, you can basically take this 1 here and put it as p plus q, p plus q squared, because p plus q is equal to 1. And then we have p plus q squared minus 4pq. Then this is p minus q squared, and so when you take the square root, it will be the absolute value. I mean, because generally we don't know which is bigger. P is greater than q, or basically is it the opposite? And of course, for the simple random walk, this will be 0. So this is the expression of FMM again, which is the summation of FMM of n. And n is a natural number. Okay, so it is basically the total, the sum. It is the probability that in some finite number of steps you will enter into state m for the first time, starting from m itself. Now what we obtained is that this is equal to 1 minus the absolute value of the difference between p and q. There is only one possibility for a random walk that will give you FMM equals to 1, which is when P is equal to Q is equal to 1/2. That's the case of the simple random walk as I did it in the previous lecture. In that case, P minus Q is 0. FMM is 1, and indeed we are talking about state that is recurrent. Now, if P is not equal to Q, the absolute value is strictly positive, and so we have 1 minus a positive quantity. So FMM will be strictly less than 1. So in that case, state M will be transient. Don't forget that our Markov chain is irreducible. Every state is accessible from every other state. So it means that if we make a judgment regarding, that this state is transient, then every guy is transient. This state is recurrent, then every guy is recurrent. Now, so we know that, in the case in which P is equal to Q is equal to 1/2, what is the mean recurrence time? What is the mean recurrence time? Because now I want to take it a step further, and rather than just saying that the states are recurrent, I want to say that the states are positive recurrent or null recurrent. Okay, positive recurrent or null recurrent. Okay, so in that case you can take the limit, and you will discover when you take the limit that actually it is plus infinity, telling you that the states are null recurrent. Okay, so this the simple random walk is a nice example in which all the states are null recurrent, and null recurrent states do not occur whatsoever in finite discrete time Markov chains. So now we have an example for them. And if P is not equal to Q, if our walk is not simple, then we are in this nice situation again that every state is a transient state. Again, an impossibility in the domain of finite discrete time Markov chains. Okay, and we did this to FMM. You can also take limits regarding things like F01. What is the probability that sooner or later you will enter into state 1 from state 0? So you will find that this probability, again, by taking limits, it's 1 if P is greater than or equal to Q, but it is strictly less than 1 if P is less than Q, which means that if P is strictly less than Q, there is a probability, okay, that which is 1 minus this P over Q, that starting from 0, you will never ever in a finite number of steps go into state 1. Okay, so what you see here is basically basically inferring information using the generating function. The nice thing here is that we successfully obtained closed form expressions for the generating functions, and thanks to the strong Markov property, and doing again the things that we have been doing, you can use these to classify the states. Okay, any question? Okay, so let's do the analysis for a more sophisticated random walk. It's a random, so the sophistication will come from being in the L-dimensional space. Okay, so imagine now a lattice, a grid in Z to the L. Okay, so it is the Cartesian product of Z with itself L times. Okay, and so it's a grid of integers in the L-dimensional space. It's basically a set of points in which basically each point has L coordinates. All of them are integers. So we will start at the origin, and now we will basically do a walk in a space of arbitrary dimensionality, but of course L is finite. Okay, so L is finite, but it can be any finite number. Okay, so we are done with L equals 1, and now we will do a general L, but of course things here will be more sophisticated, so we will focus just on a simple random walk, which means that your steps are equiprobable. So if you move, the likelihood of moving in a certain direction is like the likelihood of moving in any other direction. Okay, so what is the story now? Now your steps your steps are vectors, and the possibilities now are 2L possibilities. Okay, so in 2 dimensions, if L is equal to 2, now if you are in state, so this is the grid, and suppose that you are in IJ. Now you have 4 possible movements. You can move in basically in 4 possible ways. In 1 dimension, to the right or to the left. Now in L dimensions, you can do 2L movements. You need to pick one of them. And for illustration, in 2 dimensions, you can either move to this point. Okay, so you increment I by 1. So basically you go here to I plus 1 nj, or you go to this point, which is I j plus 1, or you can go to this point, which is I minus 1 nj, or you can go to this point, which is I nj minus 1. Okay, so your possibilities are those 4 neighbors. And by neighbors, I mean direct neighbors. You know, basically you are prohibited from moving diagonally. Okay, of course, I mean, I am sure that the literature and textbooks, they have a study of, you know, what if you can move diagonally. I mean, you know, you can have again a full course on random walks alone. But here I will just consider that you move basically in directions that are parallel to the axes, the coordinate axes. Okay, so you do not move diagonally. And generally, if you are living in L dimensions, then you have the possible number of steps. You can pick up the first dimension and you can add 1 to it or subtract 1. You can go to the second dimension and you can, so like here, you can you can choose to move in the horizontal direction, and then from I you go to I plus 1 or I minus 1, or you can choose to move in the vertical direction and you go to J minus 1 or J plus 1. Generally speaking, you will choose a dimension, and then in that or direction, you will have either to go plus 1 or minus 1. So that's the reason that we have 2L possibilities for your step. And it's a simple walk, and so basically each one can occur with probability 1 over 2L. And the special case will be L equals 1, and the probability of going, now this will be the probability of going to the left or to the right, and the probability will be 1/2. Okay. Now we will analyze things a bit different. So we try to learn some new things here. We will basically use the P probabilities, but in a way that is different from the derivation I did in the previous lecture. So let's see what is going on. So I will make use of the characteristic function. So we did not use the characteristic function previously. Now we will use it. The characteristic function of dk. So basically our random walk will be a summation. So x of n will be summation k from 1 to n dk. And now we are summing those L dimensional vectors. Okay, so now, and each L, you know, each dk, it's one of those vectors with probability 1 over 2L. What is the characteristic function of dk? What is the characteristic function of dk? Well, I mean, the characteristic function has a definition. Now, if you are talking about, so dk now is a random vector. Okay, so now dk is not a random variable as in the previous lecture. So it is a random vector. Okay, and so it is basically composed of L random variables. Okay, which are dk of 1, dk of 2, and so on. And so to take the characteristic, to compute the characteristic function of a random vector, you have a function that depends on, you know, so you have here how many random variables, L random variables. Then our characteristic function, its parameter u is actually a vector with L parameters. So we have u1, u2 up to ul. It's a multivariate characteristic function, and it is defined as such. It is expectation e to the I u1 dk1. So that's the first component in the step vector up to I ul dkl. Okay. Now, what are basically what is this? What is this expectation? Notice, the law of the unconscious statistician. Basically, to compute the expectation, what do? You basically replace the d's by all their possible values, and you multiply by the respective probability. So, what is this expectation? Well, the d's can be from this vector, right? And so in this vector, every component is 0 except one component which is equal to 1. And this happens with probability 1 over 2L. So 1 over 2L e to the I u1 multiplied by 1, and then plus I u2 multiplied by 0, and then plus I ul multiplied by 0. And so the survivor will be e to the I u1. And then what is the second possibility? For our basically vector dk, the step taken at instant k. Well, you may in the first direction or first coordinate, you can take the step, but now you can make it -1. So this will be plus 1 over t 2l, and then e to the I u1, and now it is -1, and the other guys are equal to 0. But you can actually choose to play, to move along the second coordinate. So this will be 1 over 2L. Now it is e to the I u1 now multiplied by 0. So I'm talking about this third possibility, plus I u2 multiplied by 1, and then the others are multiplied by 0, and so on. You do it, you get this quantity. And the sum of each two exponentials, each two guys can be combined as 2 cosine u1, 2 cosine u2, and so on and so forth. The 2 will eliminate this 2 here, and then basically the characteristic function of dk, which is the step now it's a vector, again, because you are changing your location, your position in the L-dimensional space. Your step vector will basically will have a characteristic function 1 over L summation k from 1 to L cosine uk. Okay, this is the random walk, is the sum of those IID steps, and as we did previously, we will start at the origin. What is the characteristic function of xn? So xn will be your location in the L-dimensional space. Well, the characteristic x of n is the sum of n IID random vectors in our case, but basically we still have the same property, that the characteristic function of the sum of n IID random vectors basically is the characteristic function of one of them raised to the power n. And so the characteristic function of x of n is this quantity here. So now we obtain the characteristic function of x of n. We didn't try to get the probability directly. We basically obtained it by using the characteristic function, and then the probability can be obtained from the characteristic function. Okay, so this is the idea. If you haven't seen it before, but it is, I think, something that is already in 241. That if you have a discrete random vector, basically our vector, each component can be 0 or 1 or -1, right? And these are basically the two L possibilities the vector can have. So basically the probability, if you have a vector, if this is general, if you have a discrete random vector, so the components are discrete random variables, then you can obtain a probability by integrating the characteristic function. And simply what you do, you want the probability that your random vector is equal to the first component is equal to gamma 1, the second component is equal to gamma 2, and so on. Basically what you do is that you take the characteristic function, multiply by e to the minus I u1 gamma 1 minus I u2 gamma 2, and so on. Note that those guys are basically the values at which you want to compute the probability. So this will be multiplied by the user, and you need to integrate. So actually what you see here is So this is a multi-dimensional integral. So this is actually integral from minus pi to pi, from minus pi to pi. We have L integrals minus pi to pi, and this du here is actually du1 up to dul. So it's multi-dimensional integral, basically from minus pi to pi. Okay, and for those of you who remember, this actually looks like the inversion formula for the discrete time Fourier transform. Okay, but for us here, what we will do is just use it. So what is the probability that x of n is equal to 0? So according to the recipe, what you will do is that you will take the characteristic function. We have the characteristic function. You will multiply it by e to the minus iu1, and then the first component here. We are basically concerned about returning to the origin, and so the first component will be 0, the second component will be 0, and so on. So basically the exponential that is in the general formula will be equal to 1 in our case here, and then we have this integral. And it's a sum of cosines raised to the power n. Does not seem to be manageable, but to classify the states, we need limits. Okay, and so perhaps this integral for an exact n is not manageable if n is 2 or more, or I don't know. But the idea is, let's basically do asymptotics. Okay, so limit, I will take the limit b00 of b00 of 2m going returning to the origin basically in an even number of steps, returning to the origin in an even number of steps. I will take this limit again, like the you are summing every coordinate. I mean, why even it's again every coordinate here. If you change it plus, by 1 or minus 1, by 1 or minus 1, right? So every coordinate will be a bunch. If you sum those guys to obtain your x of n, each component of x of n will be a sum of zeros or ones, and or zeros or ones and minus ones. You need the ones and minus ones basically to be at every time instant. One component will be 1 or minus 1. Note that there is no vector that contains all zeros. Again, it's because that till now we do not allow self-transitions or remaining in the same state if you are basically doing the random walk. Okay, so every component, if you want every component to be 0, then you need, again, as we did previously, we need an even instant of time. So just for illustration, in 2 dimensions, suppose that you start in 0. Okay, so at step 1 you will be either here or here or here or here. You are never in 0. Okay, can you be in 0 in step 2? Yes. Can you be in 0 in step 3? In step 3, you will find that no, it can never happen. Okay, same argument as I did in the one-dimensional case. So the limit here is the limit of this integral. Okay, it's the limit of this integral. And limits and integrals do not always commute. But we are lucky, because now this, so the integrand, okay, so integrand is upper bounded by 1, right? So the sum of cosines is between 1 and minus 1, their sum divided by L, this is 1 at most. In magnitude this thing, so magnitude of integrand is upper bounded by 1, okay, regardless of m. To be able to apply the dominated convergence theorem, you need an upper bound that does not depend on the variable with respect to which you are taking the limit. So we can upper bound this thing by 1. And what's the integral? If the integral is converging or diverging. If you integrate just 1, it's a nice integral. It's an integral basically from minus, everyone is from minus pi to pi. So you will get a finite result. Okay, so the integral from minus 1 by the u, let's say j, this one is equal to 2 pi. You know, you will get 2 pi raised to the power whatever, but the point is that this is finite. So, you know, so the integral will be, or let's put to the power L, and this will be a finite number. So we can actually apply the, you know, the dominated convergence theorem and move this limit inside. And if you move the limit inside, then basically this function is 0, except on a set of measure 0. So if it happens that all the u's are equal, all the u's, for example, are equal to 0, then this sum will be equal to 1. However, you know, basically, you know, this summation divided by L is exactly equal to 1 or minus 1 on a set of measure 0. So basically, the integral is blind to whatever is going on a set of measure 0. Outside that set, basically this quantity is strictly less than 1, and it is raised to a power which we are taking to infinity, so this thing will go to 0, and the integral of 0 is 0. So the limit is 0. The limit is 0, and so the states are transient or null-recurrent. And we know, for example, that in one dimension, the states are null-recurrent. Okay. But which is which? Which is, you know, in other words, that basically this is a result, okay, that is, you know, I want like something like in L dimensions, what do we have? So from previous studies, L equals 1, it's not recurrent. But our ambition now is to basically give me an L, and I will tell you whether the states are not recurrent or transient, or so. The states are, for a simple way, we prove this. I mean, we prove this in 2 ways. Actually, 2 ways. We prove that basically the limit, okay, so in one dimension, we did something like this. The difference here is that when I did the one-dimensional case, I actually wrote down this probability. So in the one-dimensional case, it's like, so in one, if L is equal to 1, this is 2m Cm, and simple, it's 1/2 to the power 1/2 to the power to the power 2m. Okay, so we wrote down this probability, and we did something, you know, bounding on the factorial, and we obtained that the limit is equal to 0. But then we did the summation. And from the summation, we were able to basically make the distinction, you know, and we discovered that if the walk is simple, if P is equal to Q is equal to 1/2, indeed the states are null recurrent. But if B is not equal to Q, basically the states are transient. And now in the first part of this lecture, I did the same thing, but studying FMM. Okay, you know, this point, it is, remember, it is 1 minus the absolute value of B minus Q. So this again in L equals 1, and so basically same conclusion. For the symbol walk, basically it is 1, and so it is null recurrent. Non-recurrent because, you know, for positive recurrent states, this limit should be something that is strictly positive. In multiple dimensions, we are focused basically on the symbol walk, in which like going in any direction is equally likely. But again, the question is for L equals 2, for L equals 3, and so on, what is going? Will the states also be null recurrent like L equals 1? We need the sum. We need to do the summation of, you know, so we need basically to do something like this, you know, so if plus infinity, then the states are non-recurrent, and if finite, then transient. Okay, so the challenge now is to decide. We do not need to compute it exactly. What we need to do to know is whether it is, whether it is some finite number or it is plus infinity. Okay, so sum. So this is the generating function. Okay. Again, like we know now that basically generating functions are very useful. You can by Abel's limit theorem, you can basically the sum. We know that basically the summation of B00, and okay, this is, you can obtain it by taking the limit as it goes to something like this. Okay, so the idea is that we will we have those probabilities, but now again, like in the one-dimensional case, the probabilities were like explicit in terms of the combination and so on. But now the probabilities are in terms of a multi-dimensional, an L-dimensional integral. Okay, and then we have an infinite summation. The infinite summation of of the generating function itself. Okay. So what can we do? I mean, we need to take a limit, and now between the limit and z, so we need to take the limit as z goes to 1. Actually, we have an infinite sum and we have an integral. We have an infinite sum and we have an integral. So first order of business before taking the limit is, are we allowed to interchange the infinite sum and integration? Okay, so we can try to basically apply Fubini. So Fubini tells you the following. It tells you, you want to basically study whether interchanging the order here is valid or not. Okay, a sufficient condition for validity is to study the magnitude. Okay, of this thing. And when you study the magnitude by Tonelli, you can basically do any order of your choice. If you get something finite, then you can go back here and interchange the summation and the integral. Let's see. What is this quantity? Now, the summation over n of the cosines is upper bounded by 1, and z that we use is strictly less than 1. So this is strictly less than 1 because magnitude z is strictly less than 1, and as I said, that the cosine. So basically, this thing is upper bounded by the magnitude of z, and the magnitude of z itself is strictly less than 1, and so this is basically something that is bounded. Now to write again, once you have this this bound, okay. So let me something. Okay, so we study the magnitude. Okay, you can study the magnitude or an upper bound on the magnitude. Again, the magnitude itself may be like difficult, but also if you have an upper bound on magnitude and then you apply the operations to it and you get a finite result, then you can interchange the order. So you can take the magnitude. Now it's very easy if you are upper bounded by the magnitude of z, and magnitude of z is less than 1. So in that case, basically the summation of the integral of the magnitude will be upper bounded by this quantity. And you can basically implement the summation or integral in any order of your choice, because now we have a real valued non-negative quantity, and you can basically move the summation inside. And because magnitude of z is less than 1, you can apply the geometric series formula, and you will basically get this finite result. You will be left with integrals that will give you 2 pi to the power L. So this is a finite result. So again, Fubini is you take the thing, the quantity, that here you are integrating, and then you are doing an infinite sum. You take its magnitude. You can work with the magnitude, or if you are, if you have hope, you can basically do an upper bound on the magnitude. And then once you do the magnitude, then you can do the operations in any order of your choice. The good news is when you get a finite number. If you get a finite number, then you can go to the original thing and interchange the order. So by Fubini, we can basically, before taking the limits, it seems a nice idea actually if we can move the summation inside. The reason is that we have a geometric series. Okay, so you have something raised to the power n. So it is very tempting that basically you want to do the sum first. Okay, and we are lucky enough that basically that this actually is justified. So it is geometric series, and basically this is what the result that we get. Okay, and now we will apply the limit as it goes to 1, because we want to know basically whether the states will be transient or null recurrent. In one dimensions, we already know that they are null recurrent, but again, like we want to solve now in terms of L. You know, for every L, I want to know the answer. So we want basically to take the limit. Okay. Now there is technicality here, which is that again you take the limit. The limit is outside the integral, and you wonder whether you can move it inside or not. So we want it to move inside. Okay, so we want basically this, we want it to be as easy as setting z here equal to 1. So, I mean, if you move the limit inside, and this is a continuous function of z, then basically, is it as easy like this? But you need to justify bringing the limit inside. So here, basically, the justification is a bit more complicated, and it's not just the dominated convergence theorem. Like we did things like this before, and all relied on the dominated convergence theorem, but here you need also the monotone convergence theorem. Okay, so this is a technicality. You can, I mean, if you're interested, you can read about it. But basically, there is another theorem that basically, if the integrand is non-negative, it must be non-negative. Okay, it must be non-negative, and it's monotonically increasing. Okay, then also you can take the limit inside. Okay, so it's called the monotone convergence theorem, and so you can apply both the monotone convergence theorem and the dominated convergence theorem, and so both of them, okay, pure fun. I mean, if you go through these steps, you will find that yes, you are justified in interchanging the order, and basically. The limit is you just put the z equal to 1, and then you have this integral here. We are not done yet. Okay, so I skipped this part. I mean, because I know that there is still some challenges. It is not just to justify the limit and interchanging the limit and integral. Now this integral is sort of a bit problematic, because what will happen at the origin of the U space. So what if you set U1, U2 up to UL equals, everyone is equal to 0. Every cosine will be equal to 1. The summation of cosines will be L. L over L is 1. 1 minus 1 is infinity. So we have a singularity. So we have a singularity near the origin. Okay. So even after doing this Fubini dominated convergence theorem, monotone convergence theorem, we are still in a situation that is not comfortable. And because of this, what we will do is basically, what is the problem? The problem, if this summation is very close to L in value, something that happens near the origin. Something that happens near the origin. So let's split this integral into two guys. A ball around the origin with some radius epsilon. Okay, so basically this is the open ball of radius epsilon centered at the origin. And then the domain of integration from which this ball is removed. And this is like a typical trick in integration, even integration in one dimension. If you have a singularity, you may basically try to isolate it. Let's say, you know, I know now what is the problem of integrating something like this. You know, if I explode to infinity, it will be because of this term. Okay, so this is actually the problematic term because it includes the origin itself, and the origin makes the denominator here equal to 0. Okay, so that's the idea of splitting, and then like arguing that this term is finite. Okay, so let's move. Any questions? Okay, so we need bounds. We need bounds so that we can proceed. And I give here basically all the details that you can dream of. Okay, so so this is one bound. So the trick here is to basically use bounds on the cosines. So we have this summation of cosine u. The idea is, I'm just telling you the idea. I mean, the details are here if you are interested. I mean, I don't think there is any problem in the homework that actually makes use of this, the details of how we do the bounding here. But the idea is, you know, that you have the sum of cosines, and you want your cosine uk to be upper bounded by something like, you know, that is some constant, some positive constant multiplied by uk squared, so that the summation will be upper bounded by the L2 norm squared of u. So this is the idea. So the idea is that rather than having this annoying summation of cosines, you want to have bounds, upper and lower bounds, that involve the L2 norm squared. And so you can show again, based on the arguments above, that this is a valid upper bound, and it means that the integrand is upper bounded by this quantity here. Now let's go to the second integral, in which there are no problems. The integral in which basically the origin is removed from. The integrand is upper bounded by this quantity, is upper bounded by that, you know, this constant, and then this 1 over the L2 norm squared. Okay, can the L2 norm squared be equal to 0? In this integral, can the L2 norm squared be equal to 0? No. Why no? Because in the space, in the L-dimensional space, we removed the part around the origin of radius epsilon. Okay, so basically magnitude of u2 in this region, in the region which is minus pi to pi, excluding the pole with radius epsilon, this is, so this guy in this region is greater than epsilon. Okay, and so its reciprocal is always less than 1 over epsilon squared. Epsilon is some suitable positive number. But again, the idea is that for vectors that are close to the origin, you know, this thing may explode. But what we are doing is that we are excluding the origin. So this integral is finite. And so our original integral is equal to some integral that basically is, the domain of integration is a ball of radius epsilon around the origin of the L-dimensional space, and then some other integral which is guaranteed to be finite. So basically, we everything will depend on that other integral. Okay, so that other integral here is the nice thing. We can upper bound and lower bound the integrand by this expression here. Okay, so you can again have bounds on the cosine, in which cosine uk, you write it like something related to uk squared. And so when you do the sum, you get the L2 norm squared. and you can have a lower bound, and you can have an upper bound. The idea now is that the upper bounds, they differ, of course. There is an extra square root 2 here, but whether or not our integral will converge or diverge depends on this integral here. Okay, so the idea is that the integral over the pole with radius epsilon of 1 over 1 minus 1 over L summation k from 1 to L cosine uk, well, this integral is upper bounded and lower bounded by a constant multiplied by this integral. And so if this guy is finite, if this integral is finite, this must be finite. And if this guy is infinity, this guy must be infinity. They converge or diverge together. And by diverge here, I mean, you can say it's actually infinity or infinite. Okay, so is this integral doable? The integral of 1 over the L to norm square? Yes. I mean, whenever you have like something involving the L to norm square, basically you can do spherical coordinates. Spherical coordinates can give you, the result basically in sort of straightforward. Okay, so the idea now is we will take that integral, and we will do change of variables, and because of the symmetry, we are just integrating something like it's so this thing is 1 over u1 squared plus u2 squared over ul squared. We have something here that only depends on the L2 norm of u, and does not depend on direction or anything. So basically, du can be written as a positive constant multiplied by r to the L minus 1 dr. So like for example, if in 3D, or let's write it like that, in 2D, you have, du1, du2 will be r dr d phi, but basically you can integrate with respect to phi and have a 2 pi. Okay, so you will get r dr, right? You will get r, some constant, let's put it like this, some constant, 2 pi r dr, 2 pi r dr, right? So in 3D, du1, du2, du3, again, you may have done this in some code. Basically, if you want to convert to basically spherical coordinates, what you will get is, so initially you will get r squared. You will get like r squared sine theta, d theta, d phi, dr. But then you find basically that your stuff, what you are integrating, does not depend on phi or phi. So basically you integrate phi from 0 to 2 pi, and then you integrate theta from 0 to pi. And so what you get is a constant. What you get will be a constant, something like 4 pi r squared. Okay. Or 3 4 by r squared dr. Moral of the story: if you are doing a conversion from rectangular coordinates to spherical coordinates, and again you don't have dependence on the angles, what will happen is that you will get a constant, and we really don't care about this constant. We are trying to make a decision. Do we have a finite value for the integral, or is it plus infinity? So there will be a constant, and we don't really care about it, but I mean, for your curiosity, I wrote down the general formula in L dimensions, and then you have r to the L minus 1. If you are in 2 dimensions, you get r. If you are in 3 dimensions, you get r squared. Generally, in L dimensions, you have r to the L minus 1. And don't forget that basically in the denominator, we have r squared. Okay, and so our integral, it will be a positive constant, and now what we care about is this integration from 0 to epsilon of r to the L minus 3 dr. And so basically this summation and this integral will converge or diverge together.